Insulation boards, convenient, maneuverable, and effortless to transport and install. Begin installation from the lowest edge for optimal board alignment. The tongue and groove design on boards ensures a tight, secure fit, enabling seamless connections and preventing heat loss. Special grooves ensure precise alignment, enhancing insulation effectiveness and structural integrity. Efficient progress is facilitated by securing the insulation boards atop the counterbatten on the rafters. Their robust nature allows easy customization using commonly available tools. This simplicity expedites the installation process, ensuring swift advancement in construction tasks. Moreover, their compatibility with standard tools streamlines adjustments, enabling precise modifications as needed during installation. This combination of sturdy materials and ease of tool-based alterations not only accelerates the workflow but also ensures accuracy and efficiency in fitting the boards to the structure, promoting a well-insulated and durable outcome. Immediate protection against rain and wind. The boards are consistently water-repellent, no additional treatment needed for cut edges. Laying out the hardware for the dock construction involves finding a level spot near the water, arranging the lumber, and positioning the respective DockEdge hardware, according to the guide found on their website. It's crucial to align the stringers, use pressure-treated 2x6s, and lay out all components meticulously for easy assembly and accuracy in building. In the pre-assembly stage, the floats are brought in to set the perimeter and align the stringers, ensuring proper placement and quantity. Howell 550 floats are utilized, with calculations based on DockEdge's flotation capacity formula. Pro tips include using deck screws to temporarily secure outer stringers, checking squareness with an X pattern, and gradually adding joists to guide float placement while maintaining room for necessary hardware adjustments. Installing the corner hardware involves precision and care. DockEdge's heavy-duty quarter-inch galvanized steel components are secured using half-inch carriage bolts. For a 16-foot dock, outside corner hardware is utilized, ensuring stability and support. Before drilling, lightly bevel the outside corners of the wood stringers with a sander to allow the steel hardware to sit flush against them. Mark hole centers to avoid damaging the floats during drilling, ensuring accuracy in placement. Using a 5/8-inch drill bit for 1/2-inch bolts provides flexibility in aligning the bolts with backer plates, allowing for flush mounting. Backer plates are crucial, sandwiching the dock framework between hardware pieces at each joint, enhancing structural integrity. Each corner requires careful drilling and installation, typically involving 48 holes for carriage bolts. Utilizing lock washers with each bolt prevents loosening over time. When affixing the hardware, a wrench is only required on the nut side due to the square flanges on the carriage bolts, simplifying assembly. With the corner hardware securely in place, the floats are then mounted using 4-inch lag bolts, requiring pilot holes and large flat washers for added stability. Throughout this process, attention to detail ensures the dock's stability, longevity, and reliability, crucial factors for its functionality and safety. To secure the floats, 4-inch lag bolts are used, requiring pilot holes for installation. Mounting the floats becomes easier if the dock is assembled upside down, facilitating access for drilling. Properly drilled and secured floats ensure stability and buoyancy, integral for the dock's functionality and safety. Mounting anchor attachments involves careful positioning and securing of connectors before installing deck boards. DockEdge chain retainers with galvanized steel chains are recommended. Proper orientation and attachment of these components ensure stability and allow for adequate slack to accommodate water level changes or waves. Detaching deck boards involves using 2.5-inch deck screws to secure 5/4-inch boards. It's crucial to note the orientation of the boards, ensuring the crown surface faces upwards to facilitate water runoff. Fastening the decking cap or crown side up helps water flow away from the deck surface, preventing pooling. The boards should be fastened securely to the dock frame, following the recommended orientation, enhancing both functionality and durability of the dock. Securing the floating dock involves various methods depending on its use. If left floating, anchoring it with at least 2 anchors is recommended. Connecting it to a stationary dock requires additional measures, such as using buffer materials to absorb wave action or employing ramp connectors for a stable and flexible connection, ensuring the dock remains secure and functional in diverse water conditions. Connecting the floating dock to a stationary one via a ramp involves meticulous assembly. DockEdge floating connector hinge kits provide a robust and adaptable linkage for accommodating water level fluctuations. Constructing a ramp with pressure-treated lumber and inside corner kits ensures a secure attachment. Aligning and affixing the hinges with 32 carriage bolts, lock washers, and nuts creates a stable connection. This method allows the floating dock to move in tandem with water levels, effectively expanding dock space. The length of the ramp varies based on the height of the stationary dock and potential water level changes, requiring attention to detail for a secure and functional connection. The construction of the 400 square meters geodesic dome at Roskilde Festival 2012 was a marvel of architectural innovation and environmental consciousness, echoing the principles set forth by the iconic American architect and designer, Richard Buckminster Fuller. This dome, a testament to resource optimization, borrowed from nature's own structural prowess. Mimicking the molecular structure found in carbon molecules, the dome's design ensured exceptional strength, stability, and maximized space utilization with minimal building materials. Its aerodynamic form not only allowed for the construction of expansive spaces, but also curtailed energy consumption by reducing heating needs, owing to its minimal surface area. Rooted in Fuller's pioneering work with geodesic structures during the 1950s and 1960s, this dome stood as a testament to his vision for a design revolution, a movement advocating doing more with fewer resources. Fuller's ethos resonated deeply with emerging hippie communities striving for affordable and resource-efficient housing, further cementing the geodesic dome as an icon of alternative architecture. The Roskilde Festival, steeped in a history partly derived from alternative living communities, embraced environmental awareness and boldly showcased this alternative architectural wonder on its grounds. The festival's ethos made it a natural and fitting location for the geodesic dome's installation. The initial construction in 2011 laid the groundwork for subsequent iterations. Crafted from separate modules manageable by 2 individuals. These modules were designed for easy assembly, disassembly, storage, and transportation. The following year, an expansion doubled the dome's size, demonstrating its adaptability and scalability. Constructed solely from plywood, The dome's creation involved intricate 3D projections and CNC cutting machines to shape the wood with precision. This method utilized the plywood's elasticity across panel points, simplifying assembly and reducing complexity. Transparent and waterproof membranes were seamlessly integrated around window holes, ensuring dry interiors and efficient drainage. During its 8-day presence at the festival, the dome became the epicenter of diverse cultural events. It served as a daytime stage for spoken word performances, storytelling sessions, and live drawing events. At night, festival-goers brought mobile sound systems, creating vibrant parties illuminated by visual projections onto the dome's inner walls. The structure's design, composed of standardized units forming a web of great circles across a spherical surface, echoed the geometry of a carbon-240 molecule, one frequency higher than the C60 molecule. With 240 panel points, this dome showcased the geometric intricacies inspired by nature's molecular configurations. As the festival unfolded, the dome transitioned from a pristine, freshly built centerpiece to a canvas for artistic expression. The Danish collective Ultragran revitalized it, transforming the dome into a mesmerizing canvas painted as a colossal color wheel for the final days of the festival. Peikko's efficient manufacturing units in Europe ensure swift and dependable production, facilitating tailored components and timely deliveries crucial for varied onshore wind turbine projects' success. Peikko's construction process for onshore wind turbine foundations is a streamlined and adaptable approach that caters to diverse project requirements. Their foundation solutions encompass comprehensive services, from initial design to assembly. The process typically begins with a collaborative phase where Peikko engages with customers to understand their specific needs. This stage involves discussing project specifications, site conditions, and any unique requirements for the foundation. Using this gathered information, Peikko customizes the foundation solution, which could include a range of components tailored to the project's needs. This might involve reinforcement bars, anchor bolts, or other structural elements required for the foundation's stability and strength. Peikko's expertise extends to providing complete reinforcement packages, encompassing both design and assembly services. Their commitment to offering a full-service solution means they can manage the entire process, ensuring a seamless integration of their components into the overall wind turbine foundation. Throughout construction, Peikko's focus remains on speed and reliability. Their efficient production units in Europe play a vital role in delivering components promptly, aiding in timely project completion. This efficiency is complemented by their expertise in assembly, ensuring that the foundation components are installed accurately and securely, meeting the highest industry standards. By offering tailored solutions, expert guidance, and a commitment to efficient construction processes, Peikko ensures that their foundation solutions align perfectly with the dynamic and demanding nature of onshore wind turbine projects. The process of assembling a timber frame wall in the construction of a wooden cabin is a pivotal stage that forms the backbone of the entire structure. Initially, planning and precise measurements are undertaken. The blueprint serves as a guiding template detailing the placement and dimensions of each component. Selecting high-quality spruce wood ensures not just durability, but also a certain level of aesthetic appeal due to its natural grain and color variations. The assembly starts with the arrangement of the base plate, commonly made of pressure-treated timber, positioned to form the wall's base. This provides a stable foundation and ensures that the subsequent components align accurately. Vertical studs, also crafted from spruce, are then erected at designated intervals, forming the vertical supports of the wall. Each stud is meticulously measured, cut, and aligned according to the architectural plans. precision is crucial here, as any misalignment can compromise the structural integrity of the wall. These studs not only provide vertical support, but also serve as attachment points for other elements of the cabin, such as the window frames and interior walls. Horizontal members, called headers, are inserted atop the vertical studs to support the weight above openings like doors and windows. Careful consideration is given to ensure these headers are appropriately sized and securely fixed to distribute weight evenly. To complete the frame, diagonal bracing might be added for added stability and to counter lateral forces. This step is crucial, especially in areas prone to high winds or seismic activity. Crafting window frames involves precise measurements, cutting and assembly to fit the cabin's design and accommodate windows seamlessly. Installing OSB for bracing reinforces structural integrity. Applying a weatherproofing membrane involves covering the cabin's exterior to shield it from moisture. Placing rodent-proof mesh ensures no unwelcome guests. Installing ventilation joists promotes airflow, preventing dampness. Fitting cladding enhances aesthetics and adds an extra layer of weather protection to the cabin's exterior. Storing panels on pallets involves arranging and securing panels above ground to prevent moisture absorption, damage, and ease of access during the construction process. Cutting posts and beams demands precision to the architectural specifications, ensuring they support the cabin's weight. Notching beams precisely accommodates floor joists, maintaining structural integrity. Cutting floor joists involves precise measurements and cuts for a seamless fit. Drilling mortises in load-bearing timber secures joints for robust support. Erecting walls involves carefully positioning and securing the assembled frames, posts, and beams per the architectural layout and plan. Installing floor joists is a pivotal step in creating a stable and level flooring system within the cabin. These joists, often made of sturdy timber, are precisely positioned and secured atop the foundational structure. Each joist is meticulously measured and spaced according to the architectural design, ensuring uniform support for the cabin's flooring. Proper installation involves securely fastening the joists to the walls or beams, creating a solid base for the cabin's interior spaces while accounting for load-bearing requirements and structural integrity. Building the roof structure involves crafting the framework that supports the roof's weight. Beams, rafters, and trusses are precisely positioned and secured to form the skeleton. Rafters provide the incline, while trusses distribute weight evenly. Once set, the structure is meticulously checked for alignment and strength. Roof insulation is then installed within this structure. It acts as a thermal barrier, regulating temperature extremes inside the cabin. Typically, insulation materials like foam boards, fiberglass, or spray foam are used, fitted snugly between rafters or trusses. Proper insulation prevents heat loss, reduces energy consumption, and ensures a comfortable living environment within the cabin. Interior insulation involves fitting insulation materials within the cabin's walls and ceilings. These materials, such as fiberglass bats or foam boards, help regulate temperature and sound, enhancing energy efficiency and comfort. Properly installed interior insulation minimizes heat transfer and maintains a cozy living space within the cabin. During assembly, prefabricated walls made of foam cement infused with steel and concrete are brought together. Steel frames are aligned, interlocking with precision. These walls are positioned and secured, creating a seamless fit. This method ensures rapid, accurate assembly while guaranteeing the structural integrity and insulation of the house. The process begins with planning and design of the roof structure. Steel trusses or frames, crucial components for roof support, are engineered off-site with accuracy and precision. These trusses are designed to fit seamlessly and interlock securely when assembled on-site. Once the prefabricated steel trusses are transported to the construction site, the assembly begins. The trusses are carefully positioned atop the walls, aligning with the predetermined layout. This step involves a systematic approach to ensure proper alignment and structural integrity. The interlocking steel trusses are securely connected and fastened together, forming the framework for the roof. This process involves bolting or welding the components together to create a robust and stable structure capable of withstanding various loads and weather conditions. Following the installation of the steel framework, roof decking materials are added. This decking serves as the base for the roof covering and provides additional structural support. It can consist of materials like plywood or oriented strand board, OSB, carefully installed over the trusses. Application of foam cement. Once the roof decking is in place, the foam cement application process begins. Specially formulated foam cement, known for its insulating and protective properties, is applied to the roof surface. This can be achieved through spraying, spreading, or pouring the foam cement mixture uniformly across the roof decking. Uniform and protective layer. The foam cement application ensures a consistent and durable layer covering the entire roof surface. This layer acts as insulation, enhancing energy efficiency, while also providing protection against weather elements, UV radiation, and temperature variations. Quality check and finalization. Throughout the assembly process, quality checks are conducted to ensure the proper alignment, structural integrity, and uniform application of foam cement. Any necessary adjustments or finishing touches are made to guarantee a robust and well-insulated roof. Additionally, the foam cement method offers environmental advantages. Its composition often includes recycled materials, reducing the environmental footprint of construction. Furthermore, the energy efficiency of foam cement houses contributes to sustainability by decreasing overall energy consumption over the building's lifespan. The adaptability of this construction method allows for customization according to specific design requirements. Whether it's low-cost housing developments or high-end luxury villas, the foam cement in combination with prefabricated steel and concrete can accommodate diverse architectural styles and functionalities. The welding process for the house frame at Hydrometal involves precision and expertise. Welders join structural components together, creating a sturdy framework for the building. Utilizing advanced welding techniques and quality materials, they ensure secure and seamless connections between beams, columns, and other elements. This welding process guarantees the structural integrity and durability of the house frame, meeting stringent quality standards. Assembling the floor with padding beneath involves laying a sturdy foundation, placing the prefabricated floor sections, and carefully installing the padding material beneath. ensure precise alignment and secure attachment, creating a resilient, comfortable, and energy-efficient flooring system ready for subsequent building assembly. Wall installation involves lifting prefabricated wall sections into place and securing them with precision. Ensure proper alignment, creating a solid and seamless structure swiftly. Hydrometals assembly of ceilings follows a process. Carefully position and secure prefabricated ceiling sections, ensuring a snug fit and structural integrity. Once installed, an additional layer of insulation is applied inside. This insulation process begins with the preparation of the interior surface. Fit insulation materials, often utilizing specialized tools to guarantee precise coverage and sealing. They ensure the insulation snugly fits between joists or beams, preventing air leakage and enhancing energy efficiency. The added layer of insulation plays a crucial role in maintaining optimal temperature regulation within the building. It serves as a thermal barrier, minimizing heat transfer and reducing energy consumption for heating or cooling. Additionally, this insulation can contribute to soundproofing, enhancing the overall comfort and functionality of the structure. The electrical system installation involves routing wiring, fixtures, and outlets, ensuring safe and functional electrical connectivity throughout. Hydrometals exterior wall finishing involves an additional layer of heat shield material for enhanced insulation and protection. Apply this shielding material onto the exterior surface, creating a protective barrier against heat transfer. The heat shield layer acts as a thermal barrier, reducing heat absorption from the external environment. This shielding not only enhances energy efficiency by minimizing heat transfer, but also reinforces the building's durability and weather resistance. It serves as an added protective layer, safeguarding the structure against temperature fluctuations and external elements, ensuring a comfortable and resilient building envelope. The efficiency of Hydrometal's prefabrication process stems from its ability to parallelize tasks. While the components are being manufactured in the factory, site preparation activities can simultaneously take place at the construction location. This parallel workflow significantly reduces the overall project timeline, allowing for swift assembly once the prefabricated elements arrive at the site. 7 and 8 Wellington Place, a monumental project in Leeds, unfolded as a testament to architectural innovation and precision. The narrative commences with the groundbreaking ceremony, a momentous event marking the initiation of a colossal endeavor. Excavators and construction crews descend upon the site, heralding the commencement of a transformative journey. Over the course of the first few months, the landscape evolves dramatically as the groundwork takes shape. The symphony of heavy machinery, the orchestrated dance of cranes, and the steady rhythm of construction activities weave together in a harmonious ballet. As the foundation takes form, the skeleton of the buildings gradually emerges from the earth. Steel frames rise skyward, each beam meticulously placed in alignment with architectural blueprints. The structure begins to manifest its grandeur, a testament to the collaborative efforts of engineers, architects, and builders. Months turn into seasons, and the development progresses tirelessly. The once barren site now pulsates with life as workers swarm over the construction site, their expertise and dedication evident in every stroke of paint and every installation. The towers start to soar, gradually revealing the sleek and modern facades that will soon define the cityscape. Amidst the ceaseless activity, milestones are celebrated. A topping-out ceremony marks the completion of the structural framework, a pivotal moment signifying progress and accomplishment. Simultaneously, the interior spaces begin to take shape, an intricate ballet of wiring, plumbing, and finishing work. As the project reaches its final stages, the scene becomes a hive of meticulous attention to detail. Glass panels glisten in the sunlight as they encase the edifice, the culmination of craftsmanship and precision. Landscaping breathes life into the surroundings, transforming the once bustling construction zone into a harmonious integration of nature and urban architecture. The Zoomlion ZL49 49-meter boom pump stands as a pinnacle of modern construction equipment, revolutionizing concrete pouring with its cutting-edge technology and impressive capabilities. At a job site, this mammoth machine commands attention, its towering presence signaling precision and efficiency in action. As the sun rises over the construction site, the 49 zlotys is already a hive of activity. Its robust build, sleek design, and agile maneuverability make it a preferred choice for large-scale projects. The crew, clad in safety gear, prepares for another day of pouring concrete, knowing that the 49 zlotys will be their reliable partner in this endeavor. The operator, perched in the ergonomic cabin, navigates the pump with finesse, leveraging advanced control systems that ensure accuracy and safety. The articulated boom, extending up to an impressive 49 meters, seems to reach for the sky, ready to deliver concrete precisely where it's needed. With a symphony of mechanical movements, the pump smoothly swings into action. The rhythmic throb of the hydraulic system resonates as it starts its intricate dance, orchestrated to perfection. The crew coordinates seamlessly as the concrete mix is poured into the hopper, eagerly anticipating the seamless flow of the viscous material through the intricate network of pipes and hoses. The ZL49's boom gracefully arcs and extends, guided by the skilled operator's deft control. It reaches over obstacles, maneuvering with precision to pour concrete into every corner of the structure. The agility of the pump belies its enormous power, showcasing the pinnacle of engineering that Zoomlion has achieved. The onlookers, including engineers, architects, and workers, marvel at the efficiency of this behemoth. Its ability to pour vast quantities of concrete quickly and accurately is a testament to the relentless pursuit of innovation in construction technology. Genböck Haus, a pioneering entity in the realm of innovative housing solutions, introduced its unique brand, microHOME, dedicated to crafting tiny houses, modular homes, and compact portable residences. Since its inception in 2015, the company has exclusively specialized in the creation of modular homes, meticulously constructed using ecological and top-tier timber frame methodologies, all within the picturesque landscapes of Upper Austria. The guiding principle: to deliver an exceptional living experience within a diminutive footprint, proudly presenting the tiny house crafted in Austria. At the heart of Genböck Haus lies their microHOME concept, encapsulating small yet fully functional dwellings that ingeniously accommodate living spaces, kitchen facilities, sleeping quarters, bathrooms, and all essential amenities. These dwellings, known as tiny houses or microHOMEs, revolutionize the conventional understanding of housing by offering a sustainable, space-efficient alternative. They embody the quintessence of mobility, being the foremost truly portable homes that can be seamlessly transported as per individual preferences or needs. What sets these microHOMes apart is their versatility. Beyond their compact size, they embody adaptability in design and usage. They aren't just homes. They are transformative spaces designed to cater to diverse needs. Whether it's for leisurely escapes as vacation homes, tranquil retreats during weekends, functional office spaces fostering creativity, seamless extensions to existing structures, or as temporary accommodations catering to seasonal tourism demands, These microHOMEs are the epitome of flexible living spaces. The craftsmanship and construction precision invested in each microHOME by Genböck Haus underscore their commitment to quality. These homes are not just about size. They represent a holistic approach to sustainable living, leveraging eco-friendly materials and innovative building techniques to minimize environmental impact. At its core, Terradec is engineered to address the perennial challenge of outdoor flooring: how to balance aesthetics, durability, and environmental impact. The system presents an approach to laying outdoor floors that champion permeability, allowing water to infiltrate the surface effortlessly. This feature isn't just a matter of convenience, it aligns with crucial environmental considerations. By permitting water to seep through, Terradec minimizes runoff, thus curbing issues related to water pooling or excessive runoff, contributing to the mitigation of urban flooding. The key to Terradec's water permeability lies in its intricate design, a meshwork of carefully constructed materials that foster a porous structure. This structure facilitates water drainage, ensuring that the floor remains not only functional but also environmentally conscious. The intricate composition of materials strikes a delicate balance, enabling the flooring to withstand the rigors of outdoor use while allowing nature to thrive unhindered beneath its surface. Moreover, the system's design isn't solely about functionality. It's also a testament to aesthetic versatility. Terradec offers a range of design possibilities, catering to various preferences and architectural styles. Whether it's for expansive outdoor public spaces or intimate residential gardens, the flexibility of Terradec's design allows for customization, ensuring that it complements the vision of any project. Beyond its immediate benefits, Terradec serves as a beacon for sustainable construction practices. Its emphasis on water permeability aligns seamlessly with contemporary environmental goals, promoting responsible land usage and reducing the strain on drainage systems. The serene village of Adanka, nestled in the picturesque landscapes of Dambovita County, witnessed the gradual rise of a new dwelling that would soon become a cherished addition to its countryside allure. The construction of a house in this tranquil setting represented not only the manifestation of architectural dreams, but also the fusion of tradition and modernity. The journey of erecting a new home in Adanka was a planned endeavor, steeped in the essence of local craftsmanship and contemporary construction techniques. It all commenced with the selection of a suitable plot, a parcel of land that would soon transform into the foundation of aspirations and family memories. The foundation's construction began with groundwork, shaping the terrain and excavating space for the basement, ensured precise measurements, laying the groundwork for a robust foundation, a pivotal start, marrying craftsmanship with structural integrity for the house in Adanka, Dambovita County. The construction of a house wall is a symphony of craftsmanship and precision, each layer meticulously laid to form the structure's sturdy embrace. It all commences with the arrangement of materials: bricks, stones, and mortar. Each brick, chosen with care, becomes a foundational piece. With the guidance of expert masons, these materials intertwine, creating a wall that not only encloses but also stands as a testament to skill and dedication. The process begins with the establishment of corners and vertical guides, ensuring a plumb and even structure. Layers of mortar mixed with precision are spread along the foundation, serving as the adhesive that binds the bricks together. The first row, known as the footer course, sets the stage for subsequent layers. Bricks aligned are placed atop this foundation, each one snugly nestled against its neighbor. The masons employ their expertise to ensure uniformity in alignment, levelness, and solidity. A tap here, an adjustment there. Each movement carries the weight of experience as the wall slowly ascends. As the layers ascend, small gaps, called joints, are deliberately left between the bricks. These gaps are then filled with mortar, completing the unity of the wall. With practiced hands, excess mortar is scraped away, leaving a smooth finish. This process continues, course after course, until the desired height is achieved. At strategic intervals, openings for doors and windows are meticulously incorporated. These spaces are precisely measured and crafted, ensuring structural integrity while accommodating the functionality and aesthetics of the house. Wooden frames crafted with precision await their placement within these carefully carved apertures. Throughout this process, attention to detail reigns supreme. Levels and plumb bobs are wielded with precision to ensure straightness and alignment. The mason's keen eyes constantly survey their work, ensuring that each layer contributes to the strength and beauty of the whole. The process of pouring house beams is a crucial step in ensuring structural stability and support within the building. These beams, typically made of reinforced concrete, play a pivotal role in distributing the weight of the structure and providing a framework for the floors above. Formwork, usually made of wood or metal, is erected to outline the shape and dimensions of the beams. This formwork acts as a mold, containing the liquid concrete until it sets and gains strength. Next comes the reinforcement phase. Steel bars or mesh, known as rebars, are strategically placed within the formwork. These reinforcement bars add tensile strength to the concrete, preventing cracks and enhancing its load-bearing capacity. Once the formwork and reinforcement are in place, the concrete pouring begins. A carefully prepared concrete mix, with the right proportions of cement, aggregates, water, and additives, is poured into the formwork. This viscous liquid fills the space, enveloping the reinforcement and taking the shape of the beams. Framing the roof is a pivotal phase in house construction, marking the transition from the structural framework to the creation of the roof's skeletal support. It begins with the installation of roof trusses or rafters, which form the framework supporting the roof structure. Trusses, often prefabricated triangular units made of wood or steel, are lifted into place and secured to the walls or supporting structures. Rafters, on the other hand, are individual beams that span from the peak of the roof to the walls, and are connected by horizontal purlins or collar ties to create the roof's shape. Once the trusses or rafters are in position, additional components such as ridge boards, which run along the peak of the roof, and eaves, which extend beyond the walls to provide overhang, are installed. These elements contribute to the stability and overall structure of the roof. After the framing is complete, the next step is sheeting the roof. This involves applying various layers to create a protective barrier and a solid base for the final roofing materials. Sheathing. The first layer is typically sheathing, consisting of plywood or oriented strand board (OSB), which is nailed or screwed onto the roof trusses or rafters. Sheathing adds rigidity to the roof structure and provides a base for subsequent layers. Underlayment. The next layer is the underlayment, a weather-resistant barrier installed over the sheathing. This layer shields the roof from moisture infiltration, acting as an additional defense against rain or snow. Flashing, usually made of metal, is applied in vulnerable areas such as valleys, intersections, and roof penetrations, like chimneys or vents. It prevents water from seeping into these critical areas, enhancing the roof's waterproofing. Plastering the exterior of a house is a process that involves applying a protective and decorative layer to the walls, enhancing their durability and aesthetics. Preparation. The process begins with thorough preparation. The exterior walls are inspected for any damages, cleaned and repaired. Loose materials, dirt, or old plaster are removed to create a clean surface. Application of scratch coat. A scratch coat, consisting of a mixture of sand, cement, and water, is applied to the walls. This coat provides a textured surface that helps the subsequent layers adhere securely. Installation of lath. Lath, usually made of metal or wood, is affixed to the scratch coat. The lath serves as a base for the plaster to adhere to, improving its grip and stability. Application of brown coat. The brown coat, a thicker layer of plaster, is applied over the lath. This coat is typically composed of sand, cement, and lime, providing further reinforcement and smoothing the surface. Finishing coat. The final layer, known as the finishing coat, is applied. This layer is finer in texture and can be customized for texture and color, offering a decorative touch to the exterior. It might be a traditional smooth finish or textured patterns, depending on the desired aesthetics. Surface preparation. The process begins with thorough cleaning and preparation. Surfaces are washed, scraped, and sanded to remove any dirt, debris, or loose paint. Repairs are made to damaged areas, and primers may be applied to ensure better adhesion. Choosing the paint. Selecting the right type and color of paint is crucial. Weather-resistant and durable exterior paint is typically chosen, considering the climate and specific requirements of the house. Application. Painting starts with cutting in. The precise application of paint to edges and corners using a brush. Then a roller or sprayer is used for larger areas. Multiple coats might be needed for full coverage, and each layer is allowed to dry before the next is applied. Detailing. Trim, shutters, doors, and other accents receive attention. The detailing work involves careful application to achieve clean lines and a polished finish. Finish and protection. Once the paint is applied, a final inspection ensures uniformity and quality. Applying a sealant or protective finish adds an extra layer of durability and shields the paint from weathering and UV damage. The basement pour marks the genesis of the home's construction. It begins with meticulous excavation, digging deep into the earth to prepare the ground for the concrete foundation. Steel rebar is strategically placed to reinforce the structure, ensuring its strength and durability. Then, a carefully mixed blend of concrete is poured into the excavated area, meticulously spread and leveled to form the foundation. This critical phase sets the stage for the entire house, providing a solid base upon which the rest of the structure will be built, ensuring stability and longevity. The garage floor pour is a crucial step in the construction process, creating the foundation for the vehicle storage area. Once the ground is prepared, a similar process to the basement pour ensues. Steel rebar is strategically placed within the excavation to reinforce the concrete, ensuring the floor's durability against heavy loads. Careful attention is paid to leveling and smoothing the concrete, guaranteeing a flat and even surface for vehicles to rest upon. Precision in this stage is paramount, as it dictates the functionality and stability of the garage space, ensuring it can withstand the weight and movement of cars and provide a solid base for the upper structure. The back patio pour involves carefully laying concrete to create a comfortable outdoor living space, often designed for relaxation, entertainment, and connecting the indoor and outdoor areas of the home. Framing load-bearing walls in the basement involves crafting sturdy structures using timber or steel. These walls bear the weight of upper floors and the roof, necessitating precision in their construction. Proper measurements, placement, and anchoring ensure the home's stability and safety, laying the foundation for the entire structural framework of the building. Floor joists, often wooden beams, are meticulously placed across the load-bearing walls, forming a supportive skeleton for the flooring. These joists are carefully spaced according to architectural plans, ensuring strength and uniform weight distribution. Once in place, sheets of plywood or oriented strand board (OSB) are laid atop the joists and securely fastened. This sheeting serves as a sturdy base for the subsequent layers of flooring, providing a smooth and even surface for the interior spaces while adding rigidity to the structure, crucial for supporting furniture, fixtures, and the daily activities within the home. Wall layout involves following architectural blueprints to mark the precise locations of interior and exterior walls. Builders use chalk lines and measuring tools to ensure accurate placement before framing begins. Framing the walls follows this layout, where wooden or steel studs are erected, forming the structural framework of the home's interior and exterior walls. These studs create the boundaries for rooms and spaces, providing support for insulation, electrical wiring, and wall coverings. A drone provides an aerial view, capturing the completed framed walls layout, showcasing the emerging structure's form and adherence to the architectural design. Subsequently, the walls are sheeted with plywood or sheetrock and then wrapped with a protective layer, typically a weather-resistant barrier. This combination shields the interior from the elements, enhances insulation, and prepares the walls for the installation of exterior finishes like siding or brickwork. Framing the roof is a critical stage where the structure transitions from horizontal to vertical, shaping the uppermost part of the house. It involves a meticulous process that requires precision and expertise. Initially, the roofing design plans are studied, and the angles, slopes, and measurements are carefully calculated. The process typically starts with installing the ridge board, a horizontal beam that runs along the peak of the roof, dictating its slope. Next, rafters or trusses are constructed and positioned according to the architectural blueprints. Rafters are sloped beams that extend from the top of the walls to the ridge board, while trusses are pre-assembled frameworks often used for more complex roof designs. These components form the basic framework upon which the roof will be built. Once the rafters or trusses are in place, collar ties or ceiling joists may be installed to provide additional structural support and prevent the walls from spreading apart under the roof's weight. These elements help distribute the load evenly, enhancing the roof's stability. Throughout this phase, precise measurements and angles are crucial to ensure the roof's integrity and proper drainage. The correct angles ensure efficient water runoff, preventing water accumulation that could potentially damage the structure. The sheathing, typically made of plywood or oriented strand board, OSB, is then applied over the rafters or trusses. This layer serves as a base for the roof covering and provides additional structural support. It contributes to the overall rigidity of the roof and acts as a solid foundation for the final roof material. Whether it's shingles, metal panels, or tiles, framing the roof requires skilled craftsmanship, as it's a pivotal stage that determines the home's structural strength and aesthetic appeal. Attention to detail and adherence to precise measurements are imperative to ensure the roof's durability and functionality for years to come. Sheeting the roof involves laying down plywood or OSB sheets over the rafters or trusses. This step provides a sturdy base for the final roofing material, adding structural support and rigidity to the roof's framework. Wrapping the roof involves applying an underlayment or roofing membrane over the sheathed roof. This protective layer acts as a barrier against moisture, such as rain or snow, preventing leaks and enhancing the roof's durability. It also helps in shielding the roof from potential damage caused by wind-driven rain. Simultaneously, the construction of the back patio progresses, with careful attention paid to grading the area for proper drainage. Materials like concrete pavers or stones are laid out and leveled to create a stable and inviting outdoor space. Shingling the roof marks the final phase of roofing construction. Roofers strategically install asphalt shingles, metal panels, tiles, or other chosen roofing materials over the underlayment. Each shingle or roofing piece is methodically placed, overlapping to form a protective barrier against the elements. This step not only provides aesthetic appeal, but also enhances the roof's functionality by safeguarding it against weather-related damage and ensuring proper water shedding. Together, wrapping the roof, building the patio, and shingling complete the exterior construction, fortifying the home against environmental factors while also creating functional outdoor spaces that add to the overall appeal and usability of the property. The porch and driveway pour are pivotal elements in completing the exterior construction of the home, offering functionality, accessibility, and aesthetic appeal. For the porch, the construction begins with careful planning and framing. Typically, wooden or concrete supports are installed to create the foundation for the porch structure. Once the foundation is set, concrete is poured and smoothed and leveled to form the porch's surface. This space is often designed to complement the house's architectural style, providing an inviting entryway or outdoor sitting area. Simultaneously, the driveway's preparation involves excavation and grading to ensure proper drainage and a level surface. A base layer of gravel or crushed stone is laid, followed by pouring concrete or asphalt to form the driveway's foundation. Skilled workers manage the pour, ensuring an even distribution of the material and a smooth finish. Expansion joints may also be added to prevent cracking due to temperature changes. Both the porch and driveway pours demand precision and attention to detail to create durable, functional, and visually appealing spaces that enhance the home's accessibility and curb appeal. The final stages of home construction encompass a flurry of tasks that shape the exterior and add crucial functional elements. The poured porch and driveway significantly enhance the property's usability and aesthetics. For the porch, the process involves groundwork and framing. A solid foundation is established, typically with concrete supports or footings. Once set, concrete is carefully poured, shaped, and smoothed to form the porch's surface. This space serves as an entryway or outdoor area, often tailored to complement the home's architectural style. Simultaneously, the driveway undergoes preparation, starting with excavation and grading to ensure proper drainage. A sturdy foundation is laid with a base layer of gravel or crushed stone. Then the chosen material, be it concrete or asphalt, is poured, managed skillfully for even distribution and a seamless finish. Expansion joints may be added to mitigate potential cracking due to temperature fluctuations. Windows play a pivotal role in both functionality and aesthetics, allowing natural light into the home while offering ventilation and views of the surroundings. These fixtures are carefully installed, ensuring a secure fit and proper sealing to enhance energy efficiency. The addition of garage doors further secures the property. These are not merely functional elements, but also contribute significantly to the home's visual appeal. They're meticulously installed, emphasizing durability, ease of operation, and complementing the home's design. As these elements take shape, the exterior undergoes its final transformations. Eaves, essential for directing rainwater away from the house, are installed. Siding envelops the dwelling, offering protection from the elements while enhancing its aesthetic appeal. The front facade receives meticulous attention, often featuring a rock finish. This detailing not only adds texture and visual interest, but also contributes to the home's overall character. Tin installation under the patio serves as a protective layer, safeguarding the structure and providing longevity to the outdoor living space. Meanwhile, the final touch of safety and visual enhancement comes with the addition of the front porch railing, completing the exterior while ensuring safety for inhabitants and visitors. This intricate orchestration of construction, from foundational pours to detailed finishings, represents the culmination of meticulous planning, skilled craftsmanship, and seamless coordination. Every step contributes to the transformation of a mere blueprint into a fully realized and functional living space. The installation of vertical elements within the construction process of the Résidence des Aubry in Saint-Denis is a pivotal phase, delineating the fundamental framework of the building. These elements encompass the placement of load-bearing walls, pillars, and supports that uphold the structural integrity of each floor. Using cross-laminated timber, CLT panels, a sophisticated construction technique is employed, ensuring both durability and sustainability in the building's design. The precision and intricacy of erecting these vertical elements involve a meticulous sequence. First, the foundation and base are prepared, serving as the stable groundwork upon which the vertical components are secured. Each CLT panel, pre-engineered and fabricated to exact specifications, is then methodically positioned and fastened, forming the framework for the walls and pillars. Skilled craftsmen orchestrate this assembly, employing both traditional craftsmanship and modern construction methodologies. They ensure the accurate alignment and interconnection of these elements, meticulously verifying measurements and angles to guarantee the structural soundness of the building. Beyond mere functionality, the installation of these vertical elements embodies an architectural narrative. It signifies the emergence of spatial divisions, delineating rooms, corridors, and communal spaces. Simultaneously, it embodies the promise of a safe and aesthetically pleasing environment for future inhabitants. Moreover, this phase doesn't merely signify the vertical growth of the building, it symbolizes progress, a tangible manifestation of the vision transforming into reality. Crafted from cross-laminated timber, CLT, these beams are positioned to distribute loads and reinforce the building's integrity. Each beam, engineered to exact specifications, is carefully hoisted into place and secured, forming the essential support system for the floors and the overall architectural design. This phase demands expert coordination, ensuring that the beams align flawlessly, contributing not just to stability, but also to the aesthetic appeal and longevity of the structure. Commencing with planning, the floor installation begins after the completion of the vertical elements. Each CLT panel, precision engineered to fit seamlessly, is methodically positioned, creating a solid base for the subsequent stages of construction. These panels, crafted with incredible strength and durability, form the fundamental floor structure. Skilled workers ensure the precise alignment and interconnection of these panels, verifying measurements and angles. This alignment is crucial not only for the structural integrity, but also for the seamless integration of utilities and services within the floor system. Furthermore, the floor installation is more than just the creation of a horizontal surface. It's the inception of living spaces, delineating rooms and corridors. Simultaneously, it's a testament to the project's commitment to sustainable design, utilizing timber as a renewable and eco-friendly material. As each floor is assembled, safety measures are paramount. Workers ensure the secure attachment of panels, adhering to stringent safety protocols throughout the installation process. Additionally, these floors are designed to bear substantial loads while offering acoustic and thermal insulation, contributing to the comfort and functionality of the future living spaces. This process unfolds once the main structure, including the floors and vertical elements, is in place. The installation of roof overhangs involves the meticulous attachment of CLT panels specifically designed to create a protective eave around the building's perimeter. These overhangs serve multiple purposes, primarily shielding the structure from weather elements such as rain, snow, and direct sunlight, while also providing additional shade and contributing to energy efficiency. Craftsmen meticulously position and secure each CLT panel, ensuring a precise fit and alignment. These panels are engineered to seamlessly integrate with the existing structure, forming a cohesive and robust extension. Attention to detail during this phase is crucial, not just for the functionality, but also for the visual continuity and architectural finesse it adds to the building. Moreover, the installation of roof overhangs represents a fusion of form and function. It's not merely a protective layer, but an architectural element that augments the building's aesthetics. These overhangs create depth and dimension, lending character to the structure while providing practical benefits, such as preventing water ingress and reducing direct solar heat gain. In addition to their protective role, these overhangs embody the project's sustainable ethos. By utilizing CLT, a renewable and environmentally friendly material, the construction aligns with eco-conscious practices. Furthermore, these overhangs can be designed to facilitate rainwater collection or accommodate solar panels, further enhancing the building's sustainability features. Throughout this phase, safety measures remain paramount. Workers operate with precision and caution, adhering to safety protocols while installing the overhangs at elevated levels.